Great, yeah, thanks for having me. Yeah, so today I'll talk about learning a visual imagination for robots. So if we look at the recent advances in generative AI, in the last year, we have tools like ChatGPT, which if you ask it how to construct AI, it'll give you these step-by-step instructions. And we also have these tools such as DALL-E, where if you give it an astronaut riding a horse, it can synthesize these photorealistic images. So what I'll talk about in this talk is how you can use generative AI for actually making decisions. And the essential idea I'll talk about is how video modeling or like generating video can kind of allow you to act in the world. So as an example, let's consider the task, put a carrot on the cutting board. And let's consider this image shown here. What you can do is you can essentially use a generative AI tool, in particular a text to video model, to synthesize a video of the robot doing this action. So this thing is entirely synthesized, but it looks very realistic. And I'll talk about how you can use this, you can convert this into actions afterwards. So here's another example. So again, this is a starting image, and then we give the model flip pot upright in the sink. And then it's able to synthesize this video of this pot getting flipped. So again, very realistic in nature. Okay, so so the first idea I'll talk about on how you can use text to video models to really infer actions in robotics is this idea of trying to get a universal policy or a policy that can act across many different environments. So the biggest issue of learning a policy across many environments is that there's a big difference between the action and state spaces in each environment. So a bimanual robot will have two arms, while a different robot will only have a single arm, and maybe a navigation robot will only be able to move forward in XY space. So the idea is we can use videos as a way to abstract decision-making across many different environments, where you can essentially use images to depict the immediate actions you want to take. And you can use text to specify arbitrary goals or tasks that you want to accomplish. So this allows you to learn a single model that can, on one hand, this is synthesized, so it can accomplish this synthetic task where it synthesizes a video of picking up this orange block and putting it next to a red block. It can also pick up these objects into this bin. And it can also, so this is the same model, it can also make these realistic plans of moving this board, as well as making these plans where you pick up a fork in the dishwasher and put it in a put it down. So essentially, you can use this idea of a text to video synthesis as a way to really describe actions across many environments and have a single model learn across all of these environments. And this also allows you to essentially use the videos on the internet as a way to directly teach your policy how to act. So by watching these videos of how people open doors, you can also train your model on this data so that like when you have a new image and a robot, you can imagine that it can leverage both your past demonstrations of how to accomplish a task, as well as the internet, as well as the videos on the internet, jointly as information to learn how to act in an environment. So the general idea is we take a text description and we take an image and we essentially generate these videos. And then once we have the videos, which are shown here, we can extract from these videos actions by using an inverse dynamics model. So you can take the current observation and the next synthesized frame, and you can directly use an inverse, a small MLP to regress the immediate action to execute to accomplish the next task. So we compared this way to make decisions compared to like directly using behavior cloning on the robot state, behavior cloning from the first state, using a behavior cloning using a transformer, behavior cloning using a diffusion model versus this like planning or like video generation to make actions. And what we found is that when we evaluated on a set of unseen tasks, as well as unseen combinations of natural language, our approach performs substantially better than existing past approaches. So this approach to use video to generate the actions you want to take allows you to really be able to solve a variety of tasks. So here are some more examples of decisions that you can make using using this approach. So you have a text command, flip the pot upright in the sink, as well as this first image. And now you can synthesize these videos each of which represent different possibilities of flipping the pot upright. You can also have put a big spoon from the basket to tray, and then again, this can synthesize different different variations of the video. And you can also have something like turn a faucet to the left. And now this can again synthesize different variations of turning the faucet to the left. And this approach in which you use this text to video synthesis to really describe the future states you want to execute to accomplish a task, and use the inverse dynamics model to regress the actions, also allows you to generalize a series of new descriptions on existing environments. So here we have this command, pick up the yellow corn. And in this particular data set, all the whenever you see this scene here, you always close the bin of close the box of the bin. Now, if you use internet knowledge, so if you use a lot of videos on the internet to pre-train this model, now you can see that this model is able to correctly pick up this corn, while this model actually just like closes the bin because that's what it's learned for. And you can also see something similar for like put the carrot on the burner, where this is a new text command that you haven't seen any data for. And by leveraging the existing videos on the internet, you can see that this method in the middle does not accurately do it, but the method on the right, the method on the right can pick up the carrot and move it to the burner. So essentially, by using this approach of using video to represent your policy allows you to use information on the internet to effectively learn policies. So in addition to using these models to really learn to represent the actions that you can do, another thing that this video generation allows you to do is also to learn world models. So what you can do now is you can also take an image, and now you can use the text to describe the exact action you want to execute. And now the video model can be seen as an environment simulator. So here on the right, we have a series of examples. So you have the start image, and then if you want to wash the bowl or shut off the water, you can basically, from the same image, visualize many different possibilities, from like put the carrot in the bowl to put the bowl down, or you can imagine cutting the carrots, and then washing the cutting board. So essentially, you can synthesize many different possibilities of the world, dependent on the text description you want. So you can see that even across a variety of different settings, dependent on the action you want, you can really like describe how to interact with the environment. And this is all a single model, but you can also see that you're able to chain these commands together, as well as just imagine various different possibilities. So another thing this really enables you to do by using this text description is a sequence of actions, is it also allows you to simulate long sequences of robot executions. So now here we have this starting scene, and we can just execute this large number of steps. So you can see that this procedure of using this video model as representing what will happen if you give it a task action really allows you to simulate the world. So what is this useful for? So by having a model, a learned model that can kind of approximate the real world, one thing you can do is you can directly take an RL policy and train it using your learned model. So normally when you execute things in the real world, it can be dangerous, especially if your policy is new, because it can trigger all these illegal actions that could break the robot or like cause you to have to reset the scene. So by being able to use this generative model as your learned world simulator, you can simulate a lot of actions. So here are these different simulations of actions. So you can simulate like place your hand above a blue cube, or push the red circle towards the center right, or slide a yellow hexagon a bit to the right, and so forth. So you can simulate all these actions, and from these actions, you can train an RL policy based off this simulation. And the benefit now is you can directly take this RL policy that has not seen any real robot data. So no need for dangerous interactions in the world or anything, or like resetting the environment or anything like that. You can just directly deploy it in the real world using the learned generative model. So these are a couple executions of like put the red scar to the blue cube, as well as move the blue cube next to the green circle and put the yellow cube towards the red cube. So you can see that across these three settings, you're able to, the model trained purely in simulation is able to execute these tasks in the real world. So the other big advantage of being able to learn a dynamics model of the world is to have the ability to plan or have a visual imagination of what you could do. So another thing you can use these video models for is this idea of tree search or imagination. So let's say you want to make a horizontal line of blocks. What you can do is you can use a vision language model to essentially predict a set of possible text actions to execute at the starting image. And then what you can do is you can use a video model as a world model. So it can kind of simulate what would happen if I were to take this text action. And then I can assess how good this text action is based off of what happened in the final frame of the synthesized video. And I can choose the one that makes the most progress to my final goal of making a horizontal line of blocks. And I can continually imagine different actions to execute in the future states and continuously generate until I get a full plan that solves this task. And once I have this video plan, I can directly use a goal condition policy to convert it into actions. So here's a visual illustration of this. So on this top, we have the starting image here, and we have the text instruction, put the fruits in the top drawer. So initially, given this first image here, my model predicts two possible actions that you could take. So on one hand, you could go and open the top drawer, and on the other hand, you can place the banana in the top drawer. And what happens is now my video model, so here, let me play it again. This video model synthesizes different possibilities of the world if I were to execute each of these actions. So these are both synthesized from my video model. And now from these two possibilities, I can assess which one is closer to putting all the fruits in the top drawer. The second action doesn't actually open the drawer, so it's much less close. So now based off my imagination, the right action to execute at this step is open the top drawer. And I can now imagine another action, which is put the banana in the top drawer. And then this successfully executes. And now I'm at another point. So now in my imagination, I've imagined that I'm in this state here, but I don't know what to exactly execute next. So on one hand, I could close the top drawer. On the other hand, I could place the apple in the top drawer, or I can place the Coke can in the drawer. Now, only this middle one makes progress towards the goal. And what happens is this video model will simulate each of these executions. And now you can take the synthesized imagination of the future world, and you can assess how close each of these are at finishing the goal, put the fruits in the top drawer. And you can select the most promising one, which is place the apple in the top drawer. And you can essentially repeat this thing until you have constructed this entire imagination of this sequence of specific actions to execute to finish this task. And now once you have the synthesized video, you can correspondingly convert it to real robot execution. So these are real executions using a goal condition policy. So you first open the drawer, then you put the banana into the top drawer. And then you also put the apple in the top drawer. And finally, you close the drawer. So this essentially allows you to use your video model as an imagination to plan these very long horizon tasks, and then directly convert these long horizon tasks into corresponding executions. So let's say I have this goal, make a line, and I have this, and I want to basically make this like visual imagination of how you can actually make these blocks into a line. So if you just directly try to train one large model, like one large video model to do this task, it isn't actually able to synthesize a realistic plan to actually make the blocks in a line. You can try to make this more realistic by having a model predict some text actions and then directly converting them into videos. But again, this doesn't really work that well. So you can't make a line still. But now this thing on the, oh, let me see. Now this thing on the right, this thing on the right uses a combination of planning. So the tree search procedure I talked about earlier to make this plan. And now you have the start image here. And this is the synthesized plan. So by imagining different possible futures or imaginations of what could happen, and then choosing the one that leads to the most progress towards the goal, you can construct this very controlled manipulation plan to actually make all of these blocks into a line. And in general, we find that the more planning you do, so like this by having this learned model and having it be kind of an imagination, the more you use it to help you choose actions, the better the performance is at different tasks. And you can also synthesize plans that are more complicated in nature. So here we have four images. So these are four different views of a scene. And we want to synthesize a plan that stacks all the objects on top of each other. So you can see that this is able to kind of simulate these pretty complex or long horizon dynamics. So that it's not completely physically accurate, but it essentially predicts a possible, feasible set of plan to actually accomplish this task. So in practice, because this plan is not perfect, what you would do is you would execute this plan for some number of steps. So because it has a rough set of actions accurate. And then based off your new observations, you construct a new plan. So your plan doesn't have to be completely physically accurate. It just needs to be accurate enough so that following it for a couple of steps gets you closer to the final goal. So here, and you can also, so once you have these video plans, like I talked about earlier, you can now convert them to actual executions. So here, let me show you. So this is an example of an execution of, so taking this video planning system, but now like actually using it for real simulation execution. So in this case, we want to manipulate all these blocks and make it into a line. So this task is hard because you have to be very precise about the control of the objects to actually make them into a line. And of course, since the video model by itself is not fully accurate, you can't just follow one video plan. So what you do is every couple of frames, you replan and make a new video plan. And the thing is, the video plans are accurate enough so that following it for a couple of steps repeatedly eventually gets you a consistent line. And you can also convert this to real execution. Right. Yes. And you can also do different tasks outside of making a line. So another task you can do is you can make it like group blocks by color. And one thing that's interesting about these executions is these tasks are quite long horizon. So they require a couple hundred to like 1,000 steps to execute, especially the make a line task. But actually, our system is fairly robust in the sense that it solves, for this make a pair task, it solves this task 95% of the time. And for these like long horizon make a line tasks, it still solves it around 30% of the time. So it's despite the long range nature of these tasks, it actually is fairly consistent. And you can also execute this in the real world. And these tasks are difficult because the blocks are actually fairly light. So you have to be very precise with your control to actually be able to manipulate the blocks effectively. So one thing we can do is we can compare this approach of using this like visual imagination to kind of planning the future with a variety of different methods that people have considered before. So one thing we can do is we can compare it with something like UniPy. So that is basically the thing I talked about at the beginning, where you just directly use the video model to synthesize a plan. And that doesn't work very well. You can use the language condition transformer, and it also does poorly. You can use something like RT2, which is a giant vision language model trained with actions. But again, it can't really solve this task. And you can also use something like PAMI. So that essentially just tries to generate a language plan that gets directly converted into policy. But that also doesn't work because the language plan is not concrete enough. It doesn't describe exactly the precise actions you need to do to make a line. It will say, move this block upwards, but there's many different possibilities of how upwards you want to move the block. So it doesn't actually allow you to solve these precise long horizon tasks. In contrast, our approach, which we call video language planning, does much, much better. So this is relative performance, but it does substantially better than all the other approaches across each of these three tasks. And it also can actually generalize pretty well to new objects. This model has only been trained on these rubber objects, but now there's three new objects. So there's a donut, the cupcake, and this yellow hexagon is actually wooden. So the dynamics are a bit different, but like by repeatedly executing it, you can accomplish this task of moving everything to the top right. Yeah, so that essentially concludes the discussion about like using these video models as a visual imagination. So one last thing I want to talk about is this idea that video models can also be adapted in a few shot manner. So all the video models I showed earlier, they're really trained on a lot of data from the particular domain of interest, which makes it harder to deploy on new robotic settings where you have very limited data. But one thing you can also do is you can actually adapt the video models to a particular domain by learning a very small domain-specific model and using this pre-trained model as your prior, where essentially it just amounts to adding the denoising prediction from the pre-trained model to a prediction from the small model. But essentially, this allows us to take this 0.7 billion parameter model and allows you to like synthesize these very realistic looking videos using an extremely small model and limited data. So it really allows you to not necessarily need so much domain specific data to be able to solve a task. And of course, these are all synthesized also. Okay, great. Yeah, so that concludes the things I wanted to talk about with respect to like using video models as a visual imagination. And I'm happy to take any questions.
I see George is asking how you ensure your planning in the pixel state actually obeys all the physics laws and dynamics in the scene.
Right. So I guess the videos don't necessarily actually obey physics. So the goal, so in general, these video plans kind of convey the rough actions you want to take in the environment to solve this task. So as long as the immediate next 5 or 10 actions are physically possible and you can actually execute them, which we use a goal condition policy to do, you can just replan with the plan. So even if they're not completely physically consistent, as long as they are roughly consistent, you can basically replan consistently. And the reason why they're roughly consistent is, well, because we have fairly powerful video models at this point, these models are roughly consistent.
So is it about sort of kind of to some extent referring to like if the task is to bring a glass, so robot brings it accurately and not breaks everything around, or it's a kind of is it the same set of problem?
Okay, yeah. So there's a question of if you use this video approach for these very precise like glass objects or something like this. Yeah, I like if the video plan is slightly off, right? Maybe you'll break something. So that is a concern. So yeah, maybe I think in the current state, these video models aren't extremely precise in the dynamics. Although we've seen like a lot of big advancements in their quality in the last like last month or so. So at the current moment, probably you don't want to use these for very precise manipulation things because they might break things. But it seems plausible that in the future, better video models could enable you to do this.
As I remember from your presentation, the best accuracy was like a little bit over 60%. Is it like sort of the current state of the art, that kind of accuracy of these kind of models?
Yeah, I mean, we got around, I think we might have gotten like 80 or 90% in one of the tasks, but yeah, I think I mean, we were using, our code base is based off Imagine Video, which is an old model, I guess at this point, it's like one year old. It's likely that with better video models, you could do much better. So yeah, we actually didn't spend that much time trying to tune the performance. We're just trying to show these are all the cool things you can do with video models. So I think you could probably do much better than our approach if you really want to like use it in an industrial setting.
Yeah, and also it depends on the task, right? With different tasks, you can achieve different levels of accuracy as well, right? I assume.
Yes, yeah.
Neeraj, do you want to ask a question?
Yeah, I'm sorry if you mentioned this in the talk, but I didn't catch this. Like, how do you map the videos back to robot actions, like transformations over the robot state space or something? How do you do that?
Right. So essentially we use a goal condition policy. So we take the current image observation and the next immediate synthesized frame, and we train a policy to predict actions to get from your current observation to this goal image.
So there's a separate model which is mapping like the videos, the generated videos back into robot actions, right?
Yes, yeah. So there's a small like goal condition policy that basically
Mhm.
takes your current observation and the first synthesized frame.
Okay. And so, there were various different representations of like of the arms or like, things inside the generated videos. Have you noticed any sort of like a difference in performance? Like, in some of the videos you were generating human arms, in others there were like, different types of like manipulators. Is there a difference in performance between like how does the performance of that model, which is like mapping back to actions, change with the generated video?
Yeah, so in general, so we found that this goal condition policy was actually fairly robust
Mhm.
to like the quality of the video. So as long as the object that moves or like the portion that's relevant, so like the gripper is accurately generated. So the goal
Mhm.
condition policy learns to pay attention to exactly the robot, the portion of the robot that's relevant. So in most of our videos, we found that the like end effector of the robot was pretty accurately synthesized. In the setting in which it is not accurately synthesized, for example, it's a human arm or something like this, then the model would not perform well.
So does that limit your ability to use like videos from the internet?
Well, so I guess if you can use videos from the internet, but you would need to, I guess like you would just have to have enough robot data so that you can accurately like imagine the end effector also. But the other thing, the other comment we had is there's one paper that I didn't actually talk about in this talk called Learning to Act for Actionless Videos. But in this paper, we actually pitched the idea that you don't even have to worry too much about the robot end effector. You just have to figure out the pose of the object that you're manipulating. So if you know that like in the start frame, this object's at this location and subsequently it's at this location in 3D transform space, then you can directly use a motion planner to actually compute the actions to do this.
I see. Well, I guess you could also just generate a bunch of video of the robot manipulating things and then I guess invert that in order to train the model that goes back to the robot actions, right?
Yeah, you could. Although I guess there's a question like I guess if the action information is already in the model, you could totally do something like that.
Okay. Thanks.
Thanks.
Yeah, but will it affect the will that data be like enough quality so that you can use for training? You know, is it kind of synthetic data, Neeraj? If like
No, I mean they would actually. I mean, at least what I was thinking was they would actually like have a robot and make it do random actions with a bunch of objects on a board. Because if ultimately you just want to learn like the inverse, like basically if you just want to learn like how to move an object from one position to the other, if you just do a bunch of random stuff with an actual robot arm and an actual board, you can learn how to like sort of achieve the same effect.
Yeah.
But it doesn't matter. I mean, I think it's just like too far off field at this point.
I see a question from Mihai. Have you seen issues where the model gets confused because an object in unusual position or obscured? Like, for example, if a spoon handle is obscured by a cup.
Yeah, so that's definitely an issue. So what we've observed is these video models seem promising as a visual imagination, but right now they have lots of issues when the start image is very different than what they've seen at training time. So we actually tried a lot of this like visual imagination stuff was just images we took off our cell phone. And what we found is in these settings, it just cannot really accurately simulate the dynamics that well, and it'll often like warp things around. So yeah, a big issue right now is these models don't seem to be able to generalize very well outside of the training data they've seen. One thought is that potentially these models that we've trained are relatively small. So if you could train really big ones on like tons of data, then that might not be as much of an issue. So it seems like our video models right now maybe are similar in quality to like maybe the first GPT paper or something like this. But potentially with a lot more skill, it could become very good.
I see another question. What are the failure modes of the policy based on visual imagination?
Right. So I guess one big failure mode of this visual imagination. I'm not sure if it's a failure mode, but one issue is that it's very slow. So if you want to do very dexterous tasks or like tasks that require pretty dynamic action, this can be problematic. Another limitation is that the physics is not fully accurate. So occasionally it will always predict that you should like the first portion of your plan is to make a block teleport over another one or something like this. And that's obviously not physically plausible. So then it will try to execute that and then it can lead to issues. So sometimes, having perfectly accurate dynamics is not necessary to have the plans be useful. But if the inaccurate dynamics causes your first portion of your plan to be inaccurate, then the model will act incorrectly, and that can lead to like just messing up the entire tasks or other problems.
I see Ray's asking about generalization. Can you generalize to other robot arms?
Yeah, that's something we found to work pretty well. So we found that once we've trained this model on this set of data, if we give it like a new robot arm, it can kind of imagine what that robot arm would do. So I do think this is one of the advantages of using video models as a action or policy representation, because to the video model, like different types of robot arms are fairly similar to each other.
Neeraj had another question. Do you want to ask?
I was just curious, like, is it easy to enrich to like extend the video model so that it's not just video? You could actually generate things like you could take into account like the force on the robot arm or um the friction of the surface, like things like that. Is it possible to extend these video models easily to contain that information?
Yeah, I think that'd be very interesting. Yeah, so in principle, the video model right now, it just uses free channels for an image. But yeah, you could also add like a force map,
Mhm.
or like yeah, or any or like even like yeah, force. Maybe you can add tactile sensing. Maybe you can add other even sensor modalities. But it seems like it's relatively easy to augment the video models with a variety of additional sensor readings. The big caveat is there's not that much data on the internet with this, so you would actually have to gather a lot of data. But from the modeling point of view, it's not difficult.
Yeah, yeah, I understand. Okay.
Actually, Yilun, I'm wondering, can you please elaborate more on like the challenges of, data collection and like just, preparing data for this kind of training? Like, what are the biggest like obstacles right now?
Right. So I guess if you so if you use just text and video pairs on the internet, YouTube has tons of video. The big issue with YouTube is that there actually isn't very good text labels with the videos. So I think what everyone's doing right now is you use like Blip or some type of vision language model to get these text captions. So once you have both of those, then like training a text to video model isn't so difficult. But there's a big issue with a lot of robotics tasks where like the image is not maybe is not the best representation for the state, right? Like probably to manipulate something dexterous, I really want tactile readings or like other sensor modalities. And now that gets a bit tricky because there just isn't that much data available. So we were inspired to use text to video modeling as a way to learn policies because there's just tons of text and video on the internet. But once you get to these other modalities that are very, very crucial for effective manipulation, there just isn't that data. And so now it would be up to like people to like go into different labs and like actually actively teleop this data, which makes it challenging.
But do you like kind of manually collect it and like then label, or just how you trying
Yeah, you
to
would probably, well,
overcome this?
so on one hand, yeah, maybe you would want to, so to some extent, you probably want to manually collect. So what you would do is you would just teleop the robot to do tasks, and then you would label that. Alternatively, you could try to use these robots to autonomously gather data. So you can essentially imagine that like you actually use these models as imagination. So you take the current image, you just ask it to synthesize a video, and then you just try to run your goal condition policy to execute it. And you take whatever footage you get is real robot footage. So you could do a combination of both of these things. But it seems like to some extent, most of our robots right now are tabletop robots. So you can't actually move the robot very easily. So if you just do this automatic data collection, you get very limited diversity because you basically only get the videos of like the objects you put on the board and the robot like just picking those up. So to some extent, you probably need to also manually gather a bunch of data or like at least set up a lot of different robots with a lot of different objects.
So is it what your guys doing, like, or like what you did for this particular training? I'm just wondering how did you approach the dataset collection
Yeah,
problem?
so in our well, so yeah, so in our in the experiments we ran here, we actually used existing data sets that people had collected for other purposes. So the video language planning paper, all of these block examples I was using, so all of this had actually been gathered like 2 years ago at Google Robotics. It's just that they never used it because whenever they tried something like RT2 or PAMI, it never worked on these long horizon tasks. So this visual imagination was the first time you could actually solve these long horizon tasks. But the big thing is we didn't gather data. If we gathered data, it would take several months. We just used existing data. So that is an issue with the approach.
Understood. I'm also wondering, maybe I missed it in the presentation. Can you sort of elaborate more on the architecture of this video language model? Just wondering, like, what is there under the hood?
Oh, yeah. So the vision language model it's just PAMI. So basically it takes in the last generated frame of the video and it basically just tokenizes it into these like image tokens. And you give the image token and text and you ask it to either predict the number of steps left until finishing the task, or you ask it to predict like what is the next text action immediately to execute?
Gotcha. And last question from me personally. What are sort of next steps? Like what you are thinking? How either this research you're thinking to move forward, or like you're working on some new research related to this problem? Just wondering like what we should expect in the next like year or two in terms of research in this domain.
Yeah, so I think that video models will be very important in robotics. So my thought is language models are very powerful because you can kind of interact with language. So you can give the language model an instruction, and then it can give you a response, and you can kind of interactively do many tasks with them. The issue when you directly try to use language models in robots is most things in the world that we execute are not describable in language. And that's why I think oftentimes videos are a lot more helpful to teach you how to do something than languages, oftentimes, or like instruction manuals. So I think for robotics, because the biggest challenge is visual motor control, I think video models will buy us a lot. So video models will teach us what are the right moves, or like if I give you a text instruction, make a cup of tea, like video models can synthesize and tell you what are the reasonable steps to do it. And it will also allow you to interact with the world. So you can imagine that as a robot, you try to do a task, like pick up something, and it turns out to be heavier than you expected. So you try to pick it up, and then it just falls. You can use that as previous context to your video model, right? And then you can have the video model try to like do in-context learning, even in a sense, right? Like it can basically use its previous context as additional context, like meta-learn to be able to solve the task, right? So video models, you can, if video models are powerful enough, you can imagine that they can do the exact same things for robotics that potentially language models could do for common text tasks. So yeah, so I think that's one area that I'm very excited about. And then overall, another one is this idea of like this video language planning, where the video model is an imagination. So I showed how you can like kind of combine this like vision language model with this video model to solve some tasks. I think it would be cool to imagine a decentralized architecture, right? So imagine you have many of these different models doing different tasks. So again, you have this video model be your imagination, right? But maybe you have a language model that has some like beliefs about what's going on in the world. It can generate some language instructions. You can have some image language model that like tries to assess how like what these language instructions represent on the image part. And then this image model can like feed to this video model. You can have an audio model that tries to map like audio to text. So essentially, this imagination thing could do lots of different things.